Most developers treat artificial intelligence as a cloud-based chatbot or a back-end API call waiting in a queue. They rarely consider that the most ubiquitous AI systems running today are actually inside cameras on street corners, processing complex neural networks directly on specialized chips without ever touching the internet. The news cycle focuses heavily on privacy and surveillance overreach regarding license plate readers. For us as engineers, we need to pivot immediately from the headlines to the architectural reality. These systems have undergone a massive engineering shift from simple rule-based scripts to edge-optimized inference pipelines running on hardware accelerators like NVIDIA Jetson or Rockchip ASICs. This transition is not just about recording video. It represents a fundamental change in how distributed data processing works at physical scale. Understanding this pivot reveals critical lessons for any data engineer building AI applications beyond the cloud. Latency, hardware constraints, and model optimization are no longer abstract concepts but daily operational realities. The stakes involve understanding why modern infrastructure demands sovereign intelligence rather than relying on centralized vendors that can become single points of failure in a crisis. To grasp what is happening under the hood, we must first dismantle the false assumption that license plate readers are merely cameras with simple software attached. They have evolved into sophisticated edge devices running cascaded neural networks directly on low-power silicon. A modern system does not simply capture an image and send it away to be processed later. Instead, it performs a three-stage deep learning pipeline locally within milliseconds of the car passing by. The first stage is car detection, often handled by a primary inference engine that identifies vehicles in the frame with high precision. The second stage, license plate localization, zooms into specific regions of interest to isolate the license plate from the rest of the vehicle's bodywork and background noise. Finally, the third stage performs optical character recognition on those isolated plates to translate visual data into text strings. This entire sequence happens in real time using optimized models like TrafficCamNet or LPRNet, running through inference engines such as TensorRT or OpenVINO that squeeze maximum performance out of limited silicon resources. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The hardware specialization driving this shift is where the engineering magic truly lies. We have moved away from sending raw video streams to general-purpose cloud servers for processing. Today's systems run on specialized system-on-chips designed specifically for AI workloads at the edge. A typical high-performance setup might utilize an NVIDIA Jetson Orin, which can process 5 concurrent 1080p video streams simultaneously, while maintaining a throughput of approximately 342 frames per second using batch processing techniques. Even entry-level hardware like the older Jetson Nano achieves roughly 9 frames per second for single-stream processing when utilizing quantized TensorRT engines. These numbers represent physical edge processing capabilities that dwarf what is feasible with cloud-dependent latency, proving that high-volume inference can happen without a network connection. This move to local inference solves critical bottlenecks related to both security and system design trade-offs. When you rely on centralized cloud processing for every frame of video captured by thousands of cameras, you create a massive attack surface. A single credential breach or vendor outage can compromise an entire fleet of surveillance devices instantly. We saw this clearly during the 2021 Verkada incident, where over 150,000 connected camera feeds were exposed due to centralized authentication failures. By shifting to edge-optimized ASICs and open-source platforms like Frigate or OpenNVR, data engineers achieve what we call sovereign AI. In this architecture, inference happens on-device, meaning the raw video never leaves local hardware unless explicitly required for storage after processing is complete. This offline-first capability removes reliance on external connectivity and mitigates botnet risks that have plagued legacy IoT devices in the past. The physical deployment layer further illustrates the depth of engineering involved here. These chips must handle precise timing requirements to capture plates moving at highway speeds, often exceeding 65 miles per hour. The system triggers specific infrared strobes operating at 10 Hz pulses on an 850 nanometer wavelength, exactly when motion sensors detect a vehicle. This requires hardware synchronization that simple rule-based scripts cannot manage. The software must coordinate with the camera sensor and lighting array to ensure the plate is illuminated perfectly for the neural network to read it, regardless of ambient light conditions or the angle at which the car passes by. This shift from cloud-dependent LPRs to edge-optimized ASICs represents a broader trend in industry adoption where data sovereignty becomes a primary design requirement rather than an afterthought. It mirrors the challenges faced by autonomous vehicle developers and industrial IoT practitioners who must balance ease of updates against the need for low latency and high security. The engineering trade-off is clear. Centralization offers easier model management, but decentralization provides resilience, speed, and privacy that cloud models simply cannot match in constrained environments. For data engineers and ML practitioners, this transition demands a new mental model. You must stop viewing AI solely as large language models running on massive clusters of GPUs accessible via API calls. Real-world deployment is often about squeezing high-accuracy inference onto low-power, heat-constrained edge devices where bandwidth is expensive or non-existent. It involves making hard choices between hardware selection, deciding whether to use an ASIC versus a general GPU, and performing model quantization to fit complex networks into the memory footprint of a palm-sized computer. The regulatory landscape reinforces this engineering pivot as well. New mandates like NDAA, Section 889, and FCC enforcement actions regarding vendor bans are pushing organizations toward open-source, self-hosted edge solutions. This is not just about compliance, it is about building systems that can operate autonomously when the network goes down or a vendor shuts off access. The standard has shifted to an offline-first inference engine that validates plate formats locally before any data ever touches a network interface. In conclusion, the story of license plate readers is really a case study in distributed system design for the AI era. It shows how software engineering must adapt when intelligence moves from the cloud back into the physical world where it is needed most urgently. By understanding these trade-offs between latency, hardware constraints, and security, you gain the perspective required to build robust applications that work reliably outside of a controlled server environment. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.